Hello everyone. Today in this little presentation, we will be talking about magnetism and current and how the two are so interwoven. If, like me, you find this subject to be rather tedious, I've decided to help explain it utilizing one of the coolest modern examples of these effects, the Japanese Chuo Shinkansen, which is their prototype magnetic levitation, or maglev, train which reaches speeds of up to 505 kilometers per hour. Its entire magnetic levitation system is based off the laws that govern magnetism and current, specifically Ampere's law and Faraday's law. Now, a large part of today's topic will be focused around the superconducting magnet. Let's explain this. Say we have this long wire here with some current I flowing like so. Ampere's law states that the line integral of the magnetic field, B, around a closed path, noted by dl, is directly proportional to the current flowing through the path. So, if we have a current in this wire on a straight path, it generates a magnetic field around the wire following the right-hand rule. We'll draw our field in green here marked by B. And imagine sticking your thumb in the direction of the current and wrapping your hand around the wire. Your fingers point in the direction of the magnetic field, so it curves like so. If you take this wire and now bend it into a circle, the magnetic field still follows the same pattern, but now you can look at a global field as well, which if you look from the side view here, you start to see something like this. Now say we have stacked a bunch of these loops to make a coil here made of some conducting wire. And say we start inducing a current through this wire flowing like this. Similarly to one loop, but stretch out across many, we form a field around this solenoid. And this solenoid, with its magnetic field, begins to look similarly to a dipole. So how does this relate to a superconducting magnet? Well, a superconducting magnet is essentially a solenoid of many loops that is operated at an incredibly low temperature, close to minus 270 Celsius. This critical temperature is when the material becomes a superconductive material, which is special because it now operates with zero resistance. This means it loses almost no energy in its operation, allowing it to run much longer, create much larger currents, and much larger magnetic fields. As we know from earlier in Ampere's law, the magnetic field is proportional to the current in the wire. And similarly, based on the direction we induce current, we can make the magnetic field facing outward have either a positive or a negative polarity. Now that we have these incredibly powerful superconducting magnets, the engineers of the train system arrange them on each side of the train, as you can see in this image. They also alternate between a northern polarity and a southern polarity, which is important for the propulsion of the train, which is a topic we will not discuss in this video. Now, if you look at this from a top view, like you see here, you can see how these magnets are arranged. If you have a northern pole facing out here, and a southern pole facing out on this side, then the magnets begin to interact with each other and essentially just form a dipole. And this looks like we have a simple bar magnet, so let's just imagine that for now. To envision how these magnets create levitation, we need to talk about Faraday's law. Faraday's law states a changing magnetic field through a coil of wire induces a voltage, or electromotive force, EMF, in that coil. This induced voltage gives rise to a current which flows through the loop. Note that the negative side here is just saying that the induced current will flow in such a way that the created magnetic field will oppose the change in magnetic flux. This is called Lenz's law. Let's envision this. So we have our magnet at rest here, which is generating a magnetic field that you can see here in green. And below it sits a loop with no current flowing through it. It's just a plain wire. When we start to move this magnet in any direction, we change the magnetic flux passing through this loop. And as we know from Faraday's law, this change induces an electromotive force, EMF. This EMF induces a current in the wire, which flows in a direction to which the current generates its own magnetic field to oppose the flux. For instance, if the magnet moves downward, the current will flow counterclockwise, like so. And with Ampere's law, in the right-hand rule, we now have a new magnetic field that is generated in this direction, creating an opposing force. If the magnet was pulled away, the current and thus some new magnetic field would also change directions. In other words, the EMF will create a current, which will create a magnetic field to resist the change. This is the most important concept for the train's levitation. The engineers of the maglev train created this design for a wire loop, a figure 8 design. This is present along the entire length of the track in the walls here. This design is special because as a magnet passes through the middle of the figure 8, it changes the magnetic flux through both loops, creating a current in both of the loops acting in opposite directions. What makes it so important is what we are going to look at below. Say our magnet here is creating a field out of the page towards us. If the magnet passes through the middle of the loop, it creates equal currents in both the top and bottom loops, which cancel each other out. But say in the next loop it drops lower, and more flux passes through the bottom loop. Well, we know from Faraday's law, this change in flux will cause more current to pass through the lower loop, overpowering the current created in the upper loop. From Lenz's law, this will cause a stronger magnetic field created in the bottom loop to oppose the magnet on the train, while also now creating a magnetic field of opposite polarity in the upper loop, pulling the magnet up more. The opposite would occur if the train goes too high. This figure 8 loop is repeated throughout the entire track, keeping the train levitating. Hopefully, this video helped explain Ampere's law, Faraday's law, with Lenz's law, and how magnetic fields and currents are so deeply interwoven, creating and affecting each other.